Okay, today we're going to look at the complex numbers. Consider the number 5 plus 2i, because 5 is a real number and 2i is your pure imaginary number. They're not like terms and can't be combined. This type of expression is called a complex number. Yesterday we talked about just a pure imaginary number. So the 2i we know is your pure imaginary number in the form b times I, where b is a real number and I is your imaginary unit. Now we're going to throw in another real number with addition and subtraction, giving us a standard form of a complex number as a plus b times I, where a is a real number and b times I, once again, is your pure imaginary number. Okay, so when you have complex numbers, you can add, subtract, multiply, and divide them by like terms. And we'll have some special things going on, but you've done these types of problems before when you were just adding and subtracting variables and constants. Like I said, we'll tweak a few things, but mostly we're going to be dealing with some like terms issues. So looking at number 1, you can see that you have your complex number, negative 11 plus 3i. And it's going to be added to another complex number, 9 plus 2i. In order to simplify this expression and put it in standard form, a plus b times I, we are going to first add the real numbers. Negative 11 plus 9 is negative 2. Then we're going to add the pure imaginary unit. 3i plus 2i is a positive 5i. And you can see that this is in standard form, a plus b times I. Now on number 3, you see that you have subtraction in the middle. Once again, do the same thing you did up here, except we're going to be subtracting our two like terms instead of adding them. So with our real numbers, we'll have 7 minus 2. 7 minus 2 is positive 5. And then with our i's, our imaginary units, we have negative 2i minus positive 6i. Negative 2 and negative 6 give us negative 8i. So we'll have 5 minus 8i. When you're multiplying, this is where things get to change just a little bit, because we know from our lesson yesterday, if you have I squared, that's actually equal to negative 1. And so anytime we have an expression we've multiplied or divided out or anything, and we end up with I squared, we can replace that term with negative 1. So if you look at number 5, you can see that we have a binomial times a monomial. So we're going to distribute to our two terms. We have 2i times 8. That's going to give us 16i. And then we have 2i times a negative 3i. That gives me negative 6, and then I times I is I squared. So as I'm looking at this, number 1, I notice that it's not in standard form. But the next thing that I see is that I squared in the expression. So I know from yesterday's lesson that I squared equals negative 1. So I'm able to take I squared and replace it with negative 1. Then I've got my minus 6 times negative 1. That's going to give me a positive 6. So I've simplified everything, but I also notice it's not in standard form. So to put it in standard form, I'm going to take my positive 6 and put it in the front, and my positive 16i will go to the back. And now I've simplified my expression. Number 7, if you'll notice, I'm multiplying together two binomials. So just like I would before with two binomials, I'm going to FOIL it out. So F stands for first, so I'm going to multiply the first numbers together. 7 times 4 is 28. O is the outer or the outside terms, so that's 7 times negative I, which is negative 7i. I is the inside or the inner terms. I times 4 is a positive 4i. And L is my last terms. Positive I times negative I is negative I squared. So after you have FOILed everything out, look for like terms to combine. You can see in the middle that you have negative 7i and positive 4i. So we have 28 minus 3i minus I squared. Let's keep simplifying by replacing I squared with negative 1. We know minus a negative 1 is a plus 1. So 28 plus 1 is going to give me 29 minus 3i. So not only is this in standard form, it's also completely simplified. So do you see from 5 and 7, we're able to replace I squared with negative 1 and further simplify our problem? So when you're going through these complex numbers and you have imaginary units, the I, if you have anything above an I, look for ways to simplify it. You know, I squared is negative 1. We can simplify I to the third, I to the fourth, I to the fifth. So keep on simplifying until you get down to I. On number 9, we have 6 minus 2i squared. Now remember, when you multiply a binomial times itself, what's going to happen is this first number is squared. 6 times 6 is 36. The middle term, 6 times negative 2i or negative 12i, is going to occur twice. And this last term, negative 2i, will become a positive 4i squared. If you have any trouble with the pattern, just rewrite it and FOIL it out. That'll work too. So using FOIL, once again, our first terms are 6 times 6, which is 36. Our outer terms are 6 times negative 2i, which is negative 12i. Our inner terms are negative 2i times 6, which is still negative 12i. And our last terms are negative 2i and negative 2i, which is positive 4i squared. See how the two middle terms are the same? When you multiply a binomial times itself, outer and inner will always match. So that's going to be 36. Add those together to get negative 24i, and replace I squared with negative 1. Now we have 36 minus 24i. 4 times negative 1 is negative 4. Combine those like terms. 36 minus 4 is 32 minus 24i. Okay, so let's flip it over on the back and let's talk about conjugates. Remember, a conjugate is going to have the same real number, it'll have the same imaginary number, but you'll have a positive in one and a minus in the other. When this happens, your outer terms and your inner terms are opposites, and therefore they'll cancel out. But let's look and see what happens when we work this out. We're going to see something very interesting here. So let's FOIL it out. 8 times 8 is 64. 8 times negative I is negative 8i. I times 8 is positive 8i. And I times negative I is negative I squared. You see these two middle numbers? Just like we discussed a moment ago, they're opposites, therefore they'll cancel out. And we have 64 minus I squared. Replace I squared with negative 1. And that'll give me 64 plus 1, which is 65. So what happens when you multiply conjugates? It's always going to be a real number answer. Now when you're dividing, think back to all the times when we had things going on in the denominator that were not supposed to be going on. Like 4 over 0. You can't have 0 in the denominator. It gives you an undefined number. If we had x over the square root of 2, well, we had to get rid of it by multiplying the square root of 2 over the square root of 2. Same thing is going to occur when you have I in the denominator. You're going to have to get rid of it. So if you just have a monomial in the denominator like you do on number 13, the only thing you have to do to get rid of it is multiply I over I. 10 times I is 10I. 2I times I is 2I squared. Replace I squared with negative 1. And then simplify to get negative 5I as your final answer. So if there's a monomial in the denominator, to get rid of the I, just multiply I over I. Because you won't change the value of the expression, you'll just get rid of the I in the denominator. So looking at number 15, once again, I've got just an I in the denominator. So to simplify this, I'm going to multiply I over I. So I'll have I times 28 minus 8I over 4I times I, which is 4I squared. Okay, now let's distribute here and here. I times 28 is 28I minus 8 times I is 8I squared. Now, everywhere that I see an I squared, I am going to replace it with -1. So I squared becomes -1 here, and I squared becomes -1 here. So I have 28I, minus 8 and -1 give me a +8, and 4 times -1 give me a -4. 4 will go into both of these terms. So if we simplify this, 28I divided by -4 is -7I. 8 divided by -4 is -2. The only problem with this solution is it's not in standard form. So let's put the constant term first and the pure imaginary number second, and we get -2 minus 7I. Looking at number 17, I have my first subtraction problem in the denominator. So anytime you have an addition or a subtraction problem in the denominator, multiplying I over I is not going to help you. Instead, you've got to use a conjugate. So here we're going to multiply 5 plus I over 5 plus I. In the numerator, we're going to multiply -2 times 5 plus I. In the denominator, I've got to use FOIL. So 5 times 5 is 25. 5 times I, -I times 5, and -I times I is -I squared. The 5I and the -5I will cancel out, giving me 25 minus I squared. Replace I squared with -1 to get 25 plus 1, which is 26. Now distribute in your numerator and you'll get -10 minus 2I over 26. 10, 2, and 26 are all divisible by 2. So since all of them are divisible by 2, I can simplify by 2. 2 into -10, 2 into 2, and 2 into 26. And this is my simplified answer. Now looking at number 19, I have 2 plus I. So the conjugate for 2 plus I is 2 minus I. So in the numerator, I'll have 7 plus 3I times 2 minus I. These are not conjugates, so they are not going to cancel out to a real number. Down here, I have 2 plus I, 2 minus I. So let's simplify and let's FOIL out my numerator. 7 times 2 is 14. 7 times -I is -7I. 3I times 2 is 6I. And 3I times -I is -3I squared, which will simplify down to 14 minus I minus 3I squared. On the bottom, 2 times 2 is 4. 2 times -I times 2, and I times -I. These two cancel out, giving me 4 minus I squared. Now let's replace my I squares with -1 in the numerator and the denominator. So what I'm left with is 14 minus I, minus 3 and -1 is a +3. Minus a -1 is a plus. 14 plus 3 is 17 minus I over 5. And that is my simplified fraction.